Hello there. So in this video, we're going to combine some of the techniques that we've been talking about in the previous few videos to help us solve systems of linear equations. In particular, today we're going to apply our row operations and moving into row echelon and reduced row echelon form in order to solve. So that's what we're going to do. We're going to begin with this example. It's a lovely example with a great many variables and more equations than we've seen so far. So we can tell this is going to be a fun one, right? Yay. I've rewritten our rules over here. So we're allowed to switch two rows. Remember, we're allowed to do that. We're allowed to multiply any row by a non-zero value, and we can add a multiple of one row to another. So that's our third rule. To get us started, we want to write the augmented matrix for this system. So let's take our time and do that. Remember, to write the augmented matrix, we just write the coefficients of each of the values. If it bothers you that there are all these blank spaces here, you can throw some zeros in as well as placeholders. I'm just going to write them in my augmented matrix this time. Okay, so I'm going to begin by just going across and writing those coefficients. So I've got -1, -6, 3, 1, 10, and 7. Then in the next row, I have zeros for the first two coefficients. So I'm going to have 0, 0, 2, another 0, 6, 2. Ooh, lots of zeros on this one. So we have 1, 2, 3 zeros to start. And then we have 1, 5, and 2. And for the last row, we have a 1, a 6, 0, -2, -6, -6. Draw a line because we had surgery to augment these matrices. And there we go. So here's our augmented matrix for this system. So as you can tell, I'm probably not going to be able to fit this whole problem on the board. So we're going to have to kind of erase and write as we go, which is not something I typically enjoy doing, but we don't really have too much of an option here. So make sure you're writing stuff down because at the end, right, we won't be able to see the full problem in one go on the board together. So just as a reminder, row echelon form means that we have only leading entries of ones. So this leading entry of a 1 is okay, but this leading entry of a -1 is not good. We're going to have to change that. Similar to this 2, not so nice. If we end up with any rows of zeros, they have to be at the bottom, and all of the leading entries have to be further to the right than any of the leading entries above. So for example, right now, these first 3 rows, they're okay because we have a leading entry here, and then further to the right and further to the right. But this leading entry is all the way on the left, so that's not so good. Basically, what that amounts to when we see it is that wherever we have a leading entry like this 2 here, everything underneath it has to be a 0. So this -1, we have something that's not a 0, so we're going to have to fix that. For this particular problem, we're going to use our row operations to get our matrix in reduced row echelon form. So what that means is not only are we going to want zeros underneath all of the leading entries, but we're going to want zeros above them as well. So while this 2 has zeros below it, and that's good news, it does not have a 0 above it. So to be in reduced row echelon form, we need a 0 there. So that's where we're headed. These are our tools to get there. So let's travel there. Let's go. So to begin, we're going to need, remember our strategy is to get a 1 up in the top left corner first, get zeros underneath it, and then move over to the next column and the next row and try and achieve the same or similar thing. In this case, we have 2 ways that we could get a positive 1 up here. We could choose to multiply this first row by a -1, or we can choose to switch the first and the fourth rows. That's the method I'm going to do. I'm going to switch the first and the fourth rows. So let's go ahead and do that. Really hope I have enough space here. So let's switch row 1 with row 4. So yeah, so I'm going to get, this now is going to be on top. So I'm going to get 1, 6, 0, -2, -6, -6. My second and my third rows are not going to change. So we're just going to get 0, 0, 2, 0, 6, 2, and then 0, 0, 0, 1, 5, 2. And now my first row is going to become my fourth row. So we get -1, -6, 3, 1, 10, 7. All right. So we have achieved our goal of getting a 1 in the top left-hand corner. Our next goal is to make sure we have zeros all underneath that. So we have a 0 here, so that's good. A 0 here, we're good here. And now we have this -1. You'll recall that in order to get those zeros, we're usually going to rely on our third operation here. So if I were to add the first row to the fourth row, this -1 plus 1 is going to end up being 0. So that's what we're going to do. Let me move these out of the way. There's some more space to write. So we're going to get row 4 plus row 1. When we do this, we're going to write the row that we're changing first. So because we're taking row 4 and 1 is being added to it, we're going to write that one first. And then I'm going to write down all the rows that don't change. So these are the first 3 rows. I'm just going to rewrite them. So we have 1, 6, 0, -2, -6, -6, 0, 0, 2, 0, 6, 2, 0, 0, 0, 1, 5, 2. And now I'm able to take my time and make sure that I do my operations correctly. So you do want to make sure you take your time with this. Arithmetical mistakes are really easy to make. It's super easy to drop a sign. Something that I almost did, actually, you can kind of see my zeros might sometimes almost look like 6s with this little dangly if they're not closed. This was really bad here. I've seen zeros turn into 6s that way midway through a problem. So make sure you're careful when you're writing down your numbers to avoid mistakes like that. So now I'm going to do -1 plus 1 is 0. Move over. -6 plus 6, also 0. 3 plus 0, 3. 1 minus 2 is a -1. 10 minus 6 is a 4. And 7 minus 6 is a 1. Okay, so our second row operation is completed. And good news, we have a bunch of zeros underneath 1 here. So that's nice, that's what we need. So now we're going to move into the next column and try and get a leading 1 if we can. There's a problem on this one though. We can't make 6 into a leading 1 because this 1 is the leading 1 and there's no way to get rid of it because all we have to work with are zeros. Everything underneath the 6 is a 0. What this means is that our second column is not a pivot column. It's not going to have a leading entry. So no problem. We just move to the next column and try and get a pivot position there. So again, we have a couple options. We have 2 rows that have a leading entry in them. So here's some of the things that I think about when that happens. I think about, okay, which one of these 2 is it easier to get a 1 in and maintain nice values? If it's row 4, then I'm going to switch them, kind of like I did here in the first step with rows 1 and 4. And if it's row 2, then I'm just going to work with row 2, keep it there, and then we'll have to use our third row operation technique to get rid of that 3. This is actually what's going to happen here. Dividing by 3 is not nice. We've got 1s and 4s. 3 doesn't go into that. But if I look at the second row, I have a 2 and a 6 and a 2. All of those are divisible by 2. So if I multiply the second row by half, I'm going to be able to get my leading entry of a 1 here. So that's what we're going to do. So I'm going to take half of row 2. Again, to make sure that I try and minimize potential errors, I'm going to copy down all of the rows that stay first, and then go back in and fill in row 2. So my first row is still 1, 6, 0, -2, -6, -6. I'm going to skip row 2 for the time being. 3 zeros, 1, 5, 2. 2 zeros, 3, -1, 4, and 1. Okay, so now for my second row, all I'm going to do is divide each value by 2. So 0 divided by 2 is 0, so those are going to stay. Half of 2 is 1. Half of 0 is 0, and then I'm going to get 3 and 1. So now we have our leading entry of a 1. Once we achieve that, we want to make sure that we have only zeros below. In this case, we have a 0 in row 3, but we have a 3 in row 4. So to get rid of this 3, I'm going to need to add -3 copies of row 2, and that will cancel out the 3. Again, I only want to add row 2. I don't want to add row 1. First of all, there's a 0 there, so that wouldn't be helpful anyway. But if I were to add row 1 to row 4, now I'm going to end up with non-zero values here, which I don't want, right? So let us do row 4 minus 3 row 2. This is where I'm going to have to erase and just hope we can remember what we did. All right, so coming in from below, we're going to do row 4 minus 3 row 2. Going to write the rows that stay the same first. So we have 1, 6, 0, -2, -6, -6. Then we're going to have row 2 stays the same. So as does 3. Okay, so we have 0, 0, 1, 0, 3, 1, 0, 0, 1, 5, 2. Next, we're going to take our time so we don't make any mistakes, and we're going to do row 4 minus 3 of row 2. So we're going to have 0 minus 0, 0 minus 0, and 3 minus 3. So all of those are going to become zeros. Then we have -1 minus 0, which is -1. 4 minus 9, because we have to multiply it by 3. So 4 minus 9 is a -5. And then 1 minus 3, because we have to multiply by -3. So 1 minus 3 is going to be a -2. All right, so with that complete, I'm going to erase this last row here. And we're just going to carry on until, I guess we're done, right? So in this case, we just got rid of the leading entry here. So now I have a leading entry in column 1. My next one is in column 2. In this row, we have one in column 3, as well as we do here. So in this case, I already have a 1 here. So I'm not going to mess with the third row. I can jump immediately to try and get rid of this -1. Because these two are the same value but opposite signs, I can just add row 3 to row 4. So row 4 plus row 3. We're changing row 4, so again, we want to write that one first. All right, 1, 6, 0, -2, -6, -6, 0, 0, 1, 0, 3, 1, 0, 0, 0, 1, 5, 2. If I do 0 plus 0, I'm going to get 0, and that's the case for these first 3 columns. -1 plus 1 is 0. -5 plus 5, 0. -2 plus 2, 0. So I don't think we've had this happen yet in any of the problems that we've been solving, where we end up with a row of all zeros. We had a couple examples earlier where this number was not 0 and these were all zeros, and that resulted in an inconsistent system. In this case, what we're getting from this 4th row is just that 0 is equal to 0. That's a true statement, so this is okay for us to have. So no problem with this row. And now our matrix is actually in row echelon form because all of our leading entries has moved to the right. So we've got column 1, 2, and then 3. Our row of zeros is at the bottom, and all of our leading entries are 1s. So we're in row echelon form. For this problem, I wanted us to go to reduced row echelon form, which we are not in yet. So recall, in order to be in reduced row echelon form, we need zeros above the leading ones as well. So this leading one, there's no row above, so we're safe here. This leading one actually has a 0 above it, so we're good to go there. And this leading one has a 0 below, a 0 above, and now we have a row that's not a 0 here. So this is the one we're going to have to change. In order to change this, we're now going to take row 1, and we're going to add an appropriate multiple of row 3 to get rid of it. This is not going to mess up any of our leading values because everything before this 1 is a 0. So everything in this row before that is going to stay the same. It's not going to change. This is why it's important to have those leading ones moving to the right. So when you add back up, you don't change anything that happened before. All right, so let's go do that. In order to get rid of this -2, we need a 2 here. So we're going to take row 1 and we're going to add twice row 3. This time row 1 is the one that changes. So I'm just going to do row 1 first, and then I'll copy everything that stays the same. So I'm going to do 1 and 0, 6 and 0, 0 and 0. As promised, these all stay the same. So we've got 1, 6, and 0. Now I'm going to get -2 plus 2, which is 0. Twice 5 is 10. So I have -6 plus 10, which is 4. Twice 2 is 4. So I've got -6 plus 4 is a -2. Everything else stays the same, so I'm just going to go ahead and copy the rest of this. And now our matrix is in reduced row echelon form. Hooray! Now that we have our matrix in reduced row echelon form, we're going to write our solution to this system of equations. To begin with, I'm just going to rewrite these in terms of the variables that we started with. I erased the original problem, but initially this was V, and then we went W, X, Y, and Z. So this first line, this first row, is going to mean V plus 6W, no X, no Y, plus 4Z is equal to -2. In the second row, there's no V, no W, so we're going to start out with X, no Y, plus 3Z is 1. And in the third row, again, no V or W, this time no X. So we just have Y plus 5Z is equal to 2. And in the fourth row, we just have zeros. So I could write 0 equals 0, but we know that I don't need to write that. So this system that initially began with 4 equations was able to reduce to a system of just 3 equations. In this case, because we have more variables than we have equations, that means we're going to have what? Do you remember? Parameters. We're going to have parameters for our solution. So remember, when we have a parameter, we want to try and see if we can get one variable or all the variables in terms of another variable. In this case, I noticed that my last two equations both involve one variable and z, which means I'm going to be able to write x in terms of z and y in terms of z. So that's what I'm going to do. This is going to become x is equal to 1 minus 3z. And then this equation is going to become y equals 2 minus 5z. So it looks like z is going to be one of our parameters because we were able to write x and y in terms of z. For this first row, I have a z, so I can move that over to the other side to get, a start of something in terms of z. But instead of just one other variable, I have two other variables to worry about now. There's no other equation to kind of help me solve this. I don't have v in either of these equations, and I don't have w in either of these equations. So what that means is we have not only one parameter, we're going to have two parameters. You can choose which one you want to be your parameter. So I could solve for w, or I can solve for v. It's a lot easier to solve for v. So I'm going to treat z as a parameter and w as a parameter and solve for v in terms of those two. So I get v is -2 minus 6w minus 4z. I'm going to make a little bit more space over here. Now, when we have our parametric solutions, we're going to use either S or T for a parameter. In this case, we need to use both because we have two parameters. So to help myself out, I like to list all of my variables in order. So I have V, W, X, Y, and Z. And then I'm going to define my parameters first. So let's use S for W and T for Z, since those were our two parameter values. So S for W and T for Z. All right, so you can do this next step in 2 steps if you want. I'm going to choose to do it in 1. What I'm going to do is I'm going to rewrite each of these equations, but instead of using W and Z, I'm going to use the new S and the T. So if you feel more comfortable rewriting these exactly as they are, and then doing another step where you then replace all the Z's with T's and all the W's with S's, feel free to do that. But I'm just going to do that as I rewrite. So V is -2 minus 6W, but W is S, so minus 6S, minus 4Z, Z is T, so minus 4T. Same thing for X and for Y. So X is going to be 1 minus 3T, and Y is going to be 2 minus 5Z, but Z is T, so 2 minus 5T. Then to write my solution, I'm going to write it in matrix form. There we go. That's our solution to the system of linear equations. Isn't that delightful? So what does the solution mean, right? All these S's and T's, we didn't get a number that doesn't look like a solution. So when you get a parametric solution, what that means is you can substitute in any value for those parameters, and that will be a solution to the system. So for instance, if I wanted T to be 0 and S to be 0, right? Both of my parameters are 0, then I would get as a solution -2, 0, 1, 2, 0. Because these would become 0, that would become 0, 0, 0, and 0. So if I were to substitute these values in for v, w, x, y, and z into my initial system, it would work for all of those equations. You can also think of this as a 5-tuple. -2, 0, 1, 2, 0, right? So like an ordered pair, but longer. So if that makes it more comfortable to help you substitute in, you can think of it in that way. But 0 was just a nice, easy number I picked. I can literally pick any number for S and any number for T, and that's going to be a solution to the system. So if I picked 1 for S and 1 for T, that would give me a new system. If I picked -pi and E, then that would give me a new solution to the system. So any real number is going to work in this case. So this process of taking an augmented matrix and row reducing using our elementary row operations until we get to row echelon form or reduced row echelon form is a process that was established by Carl Gauss way back in the day. And so because of that, this process is going to be named after him. So let's do a definition to define what this process is. Here's our definition 6. This process of finding the reduced row echelon form to solve a linear system of equations is called Gauss-Jordan elimination. If you use row operations to find a matrix in just row echelon form, and solve with back substitution, it's called Gaussian elimination. Nice and brief, this definition, right? We've defined 2 terms. Again, we've defined Gauss-Jordan elimination. And we've defined Gaussian elimination. As I alluded to before, this process is named after Carl Gauss. He is one of the most prolific and phenomenal mathematicians in the history of math. Like when you think about what Newton and Einstein did for physics, that was Gauss for math. His hands are like everywhere, especially in algebra. Jordan was not really so much a mathematician. He just kind of came along and it's named after him. I don't really know why. But Gauss is sort of the one who established this process. If you really want to feel like you haven't accomplished enough in your life, read the Wikipedia page on Gauss and you will weep and then say, it's all right. It's okay, I am enough. So what this means, what's the difference between these 2 processes, right? So Gauss-Jordan elimination is what we just did in that last example. We took our augmented matrix and we used our row operations to reduce it to reduced row echelon form. So Gauss-Jordan elimination, you have to go all the way to reduced row echelon form. For Gaussian elimination, you can be a little bit sloppier. You only have to go to row echelon form for Gaussian elimination. What that means is you're likely to have to do a little bit more solving after after you get your final matrix, but it means you don't have to rewrite the matrix a million times. So it can actually be a little bit quicker to do that solving than to do all of those row operations to get like a perfectly reduced system. So because we did the last example using Gauss-Jordan elimination, let's use Gaussian elimination for this next example. For this example, I've opted to go for a fewer variables and equations. So we only have to worry about 3 variables and 3 equations on this example. We're going to begin, as always now, writing the augmented matrix for this system. I'm going to write them in columns this time. It'll just help me keep things a little bit neater to begin with. So I have 1, -1, 3, 1, -2, -7, 2, 3, 4, 8, 1, and 10. Now remember our plan of attack. Our plan of attack is to make sure we get a 1 in the top left-hand corner. We have that, that's fabulous. And then what do we need to do after that? So we're going to need to get zeros underneath that 1. In this case, I have to fix both rows. So far, all of our rows, all of our previous examples, we really only had to fix 1. This time we have to fix 2. So I'm going to do row 2 plus row 1. That's going to give me a 0 here. And then after I do that, I'm going to do row 3 and subtract 3 copies of row 1. So I recommend, so how about, why don't you pause the video, do that on your own, and then I'm going to do that on the board, and then you can reconvene, and we'll check our work, make sure my work is right and your work is right, and we'll be good to go. Cool. Welcome back. How did you do? So this was my result after my first row operation. So row 2 is the one that changed. I got 0, -1, 5, and then 9. And then after my next row operation, row 3 is the one that changed. So I got 0, -10, -2, and -14. And this is going to result in me having a 1 and then 2 zeros underneath it. Now what? What do we do after that? Right, we're going to repeat this process. So we had a 1 in the top left-hand corner. So now we want to get a leading entry of 1 here. The easiest way I think to do this is to multiply this row by a -1. And then we'll be good to go. So we're going to do negative row 2. And this isn't too bad. All that's going to change is the sign. So I'm just going to run right through that. Fantastic. Now what? Well, we need to get zeros underneath that leading entry as we did before. So I'm going to take row 3 and add 10 copies of row 2 to it. And that's going to make sure that I get a 0 in this spot. All right, we're going to go ahead and do that. Row 3 plus 10, row 2. The first 2 rows stay the same. Zero and 0 is 0. -10 and 10 is 0. -2 minus 50 is -52. oh gosh, negative 14 minus 90 is going to be a negative 104. Now, if we were using Gauss-Jordan elimination, my next move would likely be to try and get a 0 above the 1 as well. However, because we're using Gaussian elimination, we don't care about the values above. We just want to be in row echelon form. We don't care that it's reduced. So this is fine for those first two rows. So we really just have one step left. Our last step is to multiply by a negative 1/52 to get rid of this. Well, to make this a 1, and then that's going to finish solving this one. So I'm going to leave my system up here. And I need that matrix so I know what my values are going to be. All right, so coming from the bottom, we're now doing negative 1/52, row 3. 1, 1, 2, 8, 0, 1, negative 5, negative 9, 0, 0, 1, and negative 104 divided by negative 52 is just 2. So that worked out nicely. We got an integer value again. Now, I like to use integer values in a presentation because it just makes it easier and we can focus on the process. That doesn't mean you're always going to get integer values. Very often you'll get fraction or decimal answers when you're doing your row reduction. Now that we've reached this stage, we are ready to solve our system. As before, I'm going to use these rows to rewrite now 3 new equations. So this first row represents the equation x plus y plus 2z equals 8, which you'll notice is identical to what we started with. We didn't even touch row 1 in this whole process, and that's okay. The next one is going to be y minus 5z equals negative 9. And then this last one is that z equals 2. With our equations written, we can solve by using back substitution. We already know that z is 2. And what I like to do, I always look at the end because that's usually, right, the one that's going to be defined, and then work my way up because our leading entry is moved to the right. So as I go up, I'm going to be solving for those values along the way. So here, since z is 2, I'm going to substitute that in for z, and that will enable me to solve for y. So we get y minus 5 times 2 is negative 9. 5 times 2 is 10. So I'm going to add 10 to both sides to get y equals 1. Now that I have z and y, I can substitute those into the first equation to get x. So x plus 1 plus 2 times 2 is 8. See, that's going to give me 4 and 1 makes 5. So x is going to equal 3. Therefore, for my final solution, I can write my matrix, make sure I'm going in order. So we have 3, 1, 2. So that'll be my final solution to the system. If I wanted to check, I would just substitute that into all 3 of my equations and it should work out. Just as practice, let's substitute it into 1. You can check the other 2 on your own. I'm going to throw it into the second equation, see what I get. So we get negative 3 minus 2 times 1, which is 2, plus 3 times 2, which is 6. Does that equal 1? Well, negative 3 minus 2 is a negative 5, plus 6 indeed gives us a 1. Hooray! To wrap up this video, I've got a question, and this time actually some answers for you after the question. Now, when we do our row reduction, it doesn't really matter, which row operations we do as long as they are correct and get us to where we want to be. So remember that sometimes we might start by switching two rows or multiplying one row by a value to get that one in the spot we want it in. So you might be wondering, if I were to do different row operations, would that have an impact on my solution? So the good news is, no, it's not going to. Let's express that formally in a definition and a theorem. All right, so here's our definition 9. We're going to say capital A and capital B are two m by n matrices. We tend to use lowercase variables for our scalar values for just the numbers, and we're going to be using capital letters to represent matrices. So if A and B are m by n matrices, so that B can be obtained from A by doing a series of elementary row operations, then A and B are equivalent matrices. If A and B are equivalent matrices, then their corresponding system of linear equations have the same solutions. In this definition, we've only defined one thing, honestly, and that's going to be equivalent. One of the things that we want to be careful about now that we are entering into like the land of grown-up math is to be careful about the difference between equal and equivalent. So equal and equivalent are no longer going to be equivalent. They're not going to be the same thing anymore. So equivalent in this case means that if I look at the two matrices, they look different. They represent, well, they look different. They have different numbers in them, but their corresponding systems are going to, if we were to graph them, they would be the same lines or planes or whatever they are that we're graphing, and they're going to have the same solutions to those systems. So if I start out with A and I do some row operations on it, and I end up with B, those two matrices are going to be equivalent. If I can't do that, then they're not equivalent. We've already been using this statement here basically this whole time. We've just sort of assumed this to be true, that if we have equivalent matrices, then their systems of linear equations have the same solutions. And we kind of talked about this when we discussed the operations that we could do on equations to solve a system. And our row operations are basically a new version of those equation operations. So everything is fine and dandy. We're allowed to do all this. Nothing bad's going to happen. So from this, we're going to end up with a theorem to close out today. Are we ready? This is our very first theorem of the semester. Isn't that exciting? Okay, so theorem 1. Every matrix is equivalent to a unique matrix in reduced row echelon form. What this means is if I use Gauss-Jordan elimination to solve a system of linear equations, and you use Gauss-Jordan elimination to solve a system of linear equations, you and I will end up with the same matrix at the end, because Gauss-Jordan is going to move into reduced row echelon form. However, if I use Gaussian elimination and you use Gaussian elimination, so now we're just in row echelon form, not reduced row echelon form, we may very well have different matrices at the end, but we're going to get the same solutions. So row echelon form is not unique. It's kind of like, I think of this kind of like fractions. So if I have, I don't know, 15 over 75, I can begin to reduce that by dividing by 5, right? So that's going to give me 3 over 15. And then that reduces further to 1 over 5. So this is one process I could use to simplify the fraction, right? However, there's another way. I mean, there's a few different ways. Suppose instead of canceling out a common factor of 5, I saw that 3 goes into both of those. So then I could say, okay, 3 goes into 15 5 times, and into 75 25 times. And then I see 5 goes into both of those. So I get my 1/5. The final reduced fraction, that's like our analogy to reduced row echelon form. Once you completely reduce the fraction, you're going to get the same answer. So once you completely get your matrix in reduced row echelon form, you're going to get the same one no matter what. However, these two are like our row echelon form. So they are kind of a nicer version than what we started with. So they're a little bit reduced along the way, but we could take different steps in getting to our final answer. So if I only go to the sort of middle step, I might get a different answer in that process. So that's what happens when you use Gaussian elimination. You might use row operations to get to 3/15, and I might use row operations that get me to 5/25. Doesn't mean we're wrong. We're going to both eventually at the end of the times get to our solution of 1/5, but we took a different way to get there. So in algebra, what happens is you invent these new objects. Like we've invented matrices now, and we've been working with them and messing with them a little bit with our row operations. So once you have a handle for your objects and how they kind of manipulate a little bit together, then you start to see, or you start to wonder, are there any properties? Is there anything interesting or fun about these things? So for instance, this theorem is one thing that's interesting about our matrices. They all can be reduced, just like a fraction can be reduced to a unique simplest form fraction. Our matrices can be reduced to a unique reduced row echelon form. That's nice. But are there any other properties or things that we should be keeping our eye out for when we're working with our matrices? And that's what we're going to talk about in the next video. So I hope you have a lovely day. Thank you for joining me for some Gauss-Jordan and Gaussian elimination. Hooray! Hello. Somebody wanted to make an appearance in the video today, so he's saying hello. We'll see how long he sticks around. So, hey there. So today, see, he's already, too much math for him already.